Okay, in this video I want to move on and talk about the Krebs citric acid cycle. It actually has lots of names. As you can see here, it's called the TCA cycle in this video, or in this image. It can be called the Krebs cycle, the citric acid cycle, the TCA cycle, the tricarboxylic acid cycle. Lots of names for it. I like to just put the two common names together though and call it the Krebs citric acid cycle. So to quickly review, how have we gotten here? We split glucose in half, turning into pyruvic acid in the step called glycolysis. Then those 2,3 carbon pyruvic acids in the presence of oxygen. Remember, the rest of your metabolism is an aerobic process. Glycolysis is anaerobic, it doesn't require oxygen. The rest of this is aerobic. So in the presence of oxygen, pyruvic acid has become acetyl-CoA. Now acetyl-CoA is going to run through this Krebs citric acid cycle. Here's a neat image of the citric acid cycle from the Basic Biological Concepts book, but I'm actually going to show you a little bit more close-up version. With this image, I want to talk about the basics of what's happening, and then I'll take you to an even more specific image. Okay, so acetyl-CoA enters the citric acid cycle. Acetyl-CoA is basically like the keystone to your entire metabolism. Whether it's alcohol, fat, some of your proteins, glucose, it's going to become acetyl-CoA before it runs through the rest of your metabolism. That's not true of all proteins, etc. But for almost everything you eat, acetyl-CoA is going to be the key to your metabolism. Okay, during the Krebs cycle, we call this a cycle because, as you can see, the last end product is actually what begins the next cycle. So it runs and runs and runs. And it's very important to remember this process must occur twice because we split glucose in half. So one glucose molecule becomes two acetyl-CoAs here. Okay, so during this process, as we run through it, you see what a couple things are happening here. 2 ATP are going to be produced. It's actually called GTP, but don't worry about that. So here we see an ATP. But again, remember, this has to happen twice. So during this step, there's going to be 2 ATP produced. For a total now, we're at 4, because during glycolysis, we had a net gain of 2 ATP. During the intermediate step, there were 0 ATPs produced. And then now during the Krebs cycle, there's 2 more ATP produced. So not much energy. But remember our casino chips. So far, we've had 2 NADHs produced during glycolysis, and then 2 NADHs produced during the intermediate step. But here, we're actually going to get, we can see 1, 2, 3 NADHs, but it's going to happen twice. So we're actually going to accumulate 6 NADHs here, each worth 3 ATPs apiece in the electron transport chain, which means that's going to be worth 18 ATPs, quite a few. And then now we have a new guy, another electron carrier. Here's an FADH2. But again, since this process must occur twice, we're actually going to create 2 FADH2s. And each one of them is actually worth 2 ATPs apiece, for a total of 4. FADH2 comes from the B vitamin riboflavin. Okay, so again, that's the big picture of what's happening during this process. We produce 2 ATPs, we produce 6 NADHs worth 3 ATPs apiece. And then we produce 2 FADH2s worth 2 ATPs apiece. Again, those are casino chips, though. We have to cash them in the next step, which is called the electron transport chain. You will also see here that we're getting rid of, let me clean this up real quick so we can focus on just one more thing. We're also removing CO2s. There's one here and there's one here. And we've already lost this guy up here during the intermediate step. But remember, this had to happen twice, so we actually lost 2 CO2s here, we lost 2 CO2s here, and we lost 2 CO2s here. What that means is, remember, glucose has 6 carbons. So every one of the carbons that started as glucose has now become carbon dioxide. We don't need the carbons for energy. We actually extract energy from the bonds holding these molecules together, these high energy compounds like glucose. So basically the CO2 you're breathing out, in a simplistic way to look at it, was the glucose that you ate for breakfast or whatever. So we've actually lost all 6 of the carbons that we started with, in a simplistic way to look at it. Okay, now we can actually see what's happening here. You don't need to know the individual steps, but so our acetyl-CoA is going to join with oxaloacetic acid to form citric acid. which is then going to be converted into isocitric acid. Here we have one of our NADHs being produced, and also we're losing a CO2 there. Next we go to ketoglutaric acid, succinyl-CoA, and again, you don't have to know these, I'm just going through them. Here we have our ATP being produced here on the bottom, succinic acid. Here we have our FADH2 being produced, fumaric acid, malic acid, and then we're back to oxaloacetic acid. So that's why it's called a cycle, because then the process goes over and over and over again. This process will never stop as long as you have enough oxygen and as long as you have enough of this substrate right here, oxaloacetic acid. When might you not have enough of that? Let's say you're on like a low carb diet and you can't produce enough of this. That would be when your body would switch to using ketone bodies for fuel. So, okay, so to quickly review, where are we now? We've done our first step, glycolysis, splitting glucose in half. We've done what I call the second step, the intermediate step, where we turned pyruvates into acetyl-CoA in the presence of oxygen. In the absence of oxygen, this pyruvate would have become lactic acid. We've now undergone the Krebs citric acid cycle. So we only have one major system left, so in the next video, we'll talk about the electron transport chain.